Hello everyone. Myself is Samdani and I am a medical student. Today we will discuss about the gases law. Have you ever seen during the high pressure or a high temperature condition a tire inflated with air is at a risk of bursting? Or climbing a mountain you start feeling problems to inhale? Have you ever questioned to yourself why is it so? With changing in physical conditions of the behavior of the gases, its behavior also deviates, okay, from its original way or from its normal way, and this behavior of the gases can be studied by various laws, and these laws are called the gas laws. Now we'll move next. All the gases are generally similar behavior when the conditions are normal, but with a slight change in the physical condition like pressure, temperature or volume, these show the deviation. These three are the state variables, you can say, and the gas laws are surrounded with these variables only. The variables of state like the pressure, volume or temperature, the gas reflects its true nature, hence the gas laws are relations between these variables. Okay, so there are four gas laws present. Now we will discuss the first gas law, that's the Boyle's law. Robert Boyle studied extensively the behavior of the gas at constant temperature in 1662. In the 16th century, Robert Boyle had studied this behavior and established a relationship between their volume and pressures. He established a relationship between the volume and the pressure. The relationship is known as a Boyle's law. Okay, and it states that under the constant temperature, when the pressure on the gas increase, its volume is also decrease. So he proposes a inverse relation between a pressure and a volume. It means that at constant temperature, the product of the pressure and the volume of a fixed amount of gas is constant. Here you can see that P is equals to K1 upon V1. In this relation, K here is a proportional constant. It has a constant value itself. But from this figure, you can see here that the molecules of these gases are providing or giving us spaces and increasing the volumes as the piston is in the upward or a normal condition. As soon as we started pushing the piston downwards, the pressure inside the gases or the molecule starts colliding between them and started increasing the pressure. But as we pushing down the piston, the volume of the gas decreasing. This is showing a inverse relation between a pressure and a volume. Okay, you understand this? Now we are moving next. If a fixed mass of gas undergoes an expansion at constant temperature, then the final volume and pressure shall be P2 and V2, and the initial volume and pressure will be P1 and V1. So according to this information, here is a relation P1 upon P2 is equals to V2 upon V1 at a constant temperature. This is the final result of the Boyle's law, the relationship between pressure and volume. Here the graph is given between pressure and volume is so here in this graph this okay wait here in this graph this vertical line is y-axis, and on a y-axis pressure is present, and this horizontal line is x-axis, and this x-axis volume is present. The graph between volume and pressure is following a hyperbola type of graph. It's a rectangular hyperbola. Okay, inverse relation. And if we move to next graph, here if we change the variables, okay, if we change the variable on the x-axis, we put 1 by volume instead of directly volume, we can get a straight line graph which start from the origin, and the slope of this graph will be k, the proportional constant. Now if we put P into V or pressure into volume on the y-axis and pressure on the x-axis, we will get a constant line. Many types of variable graphs are there and they are present in your reference book. You can see that from there and you can learn more and more graph, how to draw a graph. So each curve here corresponds to different constant temperature, and is known as isotherm. Higher curve correspond to higher temperature. It should be noted that the volume of the gas doubles if the pressure is half, right? So that's all about Boyle's law. Now we are moving to Charles' law, the second law, okay? J. Charles, a French chemist, studied the behavior of the gas at constant pressure. Now, in the Boyle's law, we learn about the behavior of the gas at constant temperature, but here we will learn about the behavior of gases at constant pressure, and formulated a relationship between volume and temperature of a gas in 1787. This relation is known as Charles' law. He did the analysis to understand the technology behind the hot air balloon flight. You know what are the hot air balloon flight? You have seen that in the mountain areas or the hilly areas. According to his finding, at constant pressure and for constant mass, the volume of the gas is directly proportional to the temperature. Here, he concluded a direct relationship between the volume and the temperature. Okay. Here in the diagram itself, you can see when T1 is at the lower temperature, okay, the volume V1 is also lower, or you can say it is lower than V2, as the temperature of T2 is also started increasing. When we increase the temperature, the molecules of the gas starting evaporated, okay, it started expansion, and due to this expansion the volume of the gas also increases as with increase the temperature, right? Okay, so they found for each degree rise in temperature, volume of the gas increased by 1 upon 273.15 of the original volume of the gas at 0 degrees Celsius. Thus, if the volume of the gas at 0 degrees Celsius and at T degrees Celsius are V naught and Vt respectively. Now let's see the relationship between volume and temperature. Okay. So here is the relation. Vt is equals to V naught plus T upon 273.15 volume. Okay. Now if we take the V naught common, then the final relation will be here. This is the final relation. Vt is equals to V naught underscore 273.15 plus T upon 273.15, right? You can calculate the end result of Charles' law here. V2 upon V1 is equal to T2 upon T1 directly. Okay, this will come in your questions. Now let's us discuss about the graphs of this law. Now let's see the now let us discuss about the graph of this law. In this graph here on the y-axis volume is given, but on the x-axis temperature is given, which is in Kelvin. So there is no issue. They will form a straight line which will originate from the origin. But as we can see on the next diagram or graph, this temperature is given in Celsius, and as we know 1 degree Celsius is equals to 273 Kelvin. So according to that, we have to draw a straight line from the negative side, minus 273 degrees Celsius, okay, to equal at that. Now here is a relationship and more graph are given there. It's a constant graph between temperature and volume, right? Oh, this graph is given wrong here. This graph is not present in this law, so you can cut it directly. Now we are moving to next law, that's a Gay-Lussac's law, also referred to a pressure and temperature law. The gas-Lussac law was discovered in 1802 by a French scientist Joseph Louis Gay-Lussac while building a air of Gay-Lussac Thermometer Gay-Lussac accidentally discovered that fixed volume and mass of the gas is directly proportional to the temperature. Here, volume is fixed or volume is constant, right? It's a third law. In the first law, in the Boyle's law, we have learned about the gases behavior at constant temperature. In the Charles law, we have learned about the behavior of the gases at constant pressure, but here we will learn about the behavior of the gases at constant volume. You can see here in the diagram itself when T1 is lesser than T2 and P1 is lesser than P2. Here this clock-like object is used to measure pressure of this gas, right? Is it at 2 atm or atmospheric pressure, and this is at lower temperature T1. But as we increases the temperature with this burner, the pressure is starts to increase to 4 atm. It starts double. Okay, now you understand this figure, right? Now next, it's a mathematical term. P is directly proportional to T, or P by T is constant K3. The temperature here is measured in a Kelvin scale, or you can say it's also called a absolute scale. The graph of the Gay-Lussac's law is called an isochore because the volume is constant here. Oh, I haven't told you that in this graph, at volume and temperature graph, the pressure is constant, and at a pressure constant, they will call, or they will known as isobars. Okay, each lines of this graph will known as isobar, and now here they will known as isochore, these lines, these graph lines, the red line, green line. Okay, so here the temperature is also given in degrees Celsius, so we have to start the line or the straight line behind at the negative side, minus 273.15 degrees Celsius, right? Now during winter, let's take the example of this law. During winter, one may find that the pressure in a tire of a vehicle decrease considerably. As the temperature in the winter start decreasing, the pressure is also decreases. It's a best example for this law. Okay. Now the next law. Next law is Avogadro's law. Okay. Amado Avogadro in 1811 combined the conclusion of Delta's atomic theory and Gay-Lussac's law to give another important gas law that's called Avogadro's law. According to him, at constant pressure and temperature, the volume of all the gas constituent an equal number of molecules. In other words, it's simply that in unchanged condition of pressure and temperature, the volume of any gas is directly proportional to the number of moles of that gas. Okay. So, do you get that? What are number of moles? Number of moles is equals to mass in kg upon molecular mass, right? And Avogadro's law, Avogadro's number. What are the Avogadro's constant? The number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23, is known as Avogadro's constant. You will find that this is a same number which you can cross while discussing the definition of mole. Okay, here is a mathematical term for this law. V is directly proportional to number of moles. Number of moles can be written as mass in kg upon molecular mass, and if you put the molecular mass on the left hand side and put the volume on the right hand side, lower side, you can get the density, and the final result here will be m upon density. Okay, m is equals to k4 into density, right? So that's all. It's there is not much thing to learn about Avogadro's law, so we are moving next. Next is ideal gas equation. Here it is a combined law, or you can say it's a universal law of all that four laws, right? In the diagram itself you can see it's a ideal gas law. P is equals to nRT, and here is a number of moles. Okay, R is the Rieber's constant. Okay, there is a specific value for R which varies in different mediums, right? And T is the temperature, P is the volume, and P is the pressure. Okay, it is a Boyle's law, it is a Charles law, and it is a combined gas law. Three laws which we have learned till now can be combined together in a single equation which is known as ideal gas equation. This is a relation between four variables and it's described the state of any gas, therefore it is also called the equation of the states. Okay, now let's us now go back to the ideal gas equation. This is a relationship for a simultaneous variation of a variables. If the temperature, volume and pressure of a fixed volume of gas vary from T1, V1 and P1 to T2, V2 and P2, then we can write this equation over here, the combined gas law. Okay, now If out of 6 the value of 5 variables are known, the value of unknown variable can be calculated from this equation of the combined gas law, right? So that's it about today's lecture. Here I have provided you a table which summarizes all the gases laws, which make you easier to learn these laws. Okay, you can learn directly from here the relations between the variables. Now hope you like my video. Okay, thank you.